All right, so hi everybody, welcome. This is our fourth review. For those of you that are here, great that you're here. If there's ever a time you can't come, I do record them. I post them on YouTube. I have all the packets from 1 through 3 over there. I have basically the notes or the information you have to know, and then I have a bunch of Regents questions with the answers attached, so that after you leave here, after I've kind of drilled everything in your head that you need to know, you can go home and practice and the answers are attached. I don't know if anybody really goes home and practices, but I like to believe that you do. Or maybe someday you will, okay, as we get closer to the Regents exam. So this is the first thing that kids miss all the time. Yes, sir? Right here. You got to sign in too, Nick. Okay? So when bonds are formed, what happens to energy? And kids think that energy is absorbed. Atoms are happier when they're bonded. That's the whole point of bonding, is to become stable. Now, we talked about stable and unstable in our last review, which was about the nucleus. This is not about the nucleus. This is stable or unstable in terms of electrons in your outer shell. Happiness is 8. If you don't have 8, unless you're hydrogen or helium or lithium, you're not happy. So you make compounds in order to get happy, in order to get that magic number in your outer shell, which is 8. So like sodium, who has Na, that's 2, 8, 1. Miserable, completely unhappy, highly reactive, so reactive you don't even find it in nature as an element. Okay? How's it going to become stable? Well, you could either say gain 7 or lose 1, but it's a metal, right? And metals are losers. If you listen to heavy metal, you're a loser, right? Not really. I don't have anything against people that listen to heavy metal, but that's just the way we remember it. If you listen to heavy metal, you're a loser. So sodium will lose 1 electron, and then look at, it's stable. So sodium is going to try to react by giving its electron away. Okay, now if it happens to run into chlorine, who's also highly unstable because it's 287, what ends up happening is sodium just transfers its electron to chlorine. And then chlorine has 8 in its outer shell, and sodium has 8 in its outer shell, and they're happy. The whole point of doing that is to become stable and form a bond. This is now a bond. Okay, you might not get why. Like if Stacy's chlorine and I'm sodium, and I give her my electron, why are we now bonded to each other? Why? Why can't I just walk away from her? I'm stuck on her like glue.
The electron is holding you there.
No, the electron's not holding me there. I gave it to her. She's got it. We are not sharing it. She has it. I lost it.
You guys are good friends.
We're not good friends. What happens to me when I lose a negative? I become positively charged, right? So me, sodium, me, the loser who listens to heavy metal, become positively charged. And Stace, because she gained the electron, she became negatively charged. And what you should know is opposites attract. So I am simply attracted. This is an ionic bond right here, a plus attracted to a minus. That's all it is. Any ionic bond is that, okay? A positive attracted to a negative. Formed by the straight up transfer of electrons. I gave it to her, she's got it, okay? But I'm happier now. And what happened to energy? It was released. When I gave that electron to Stacy and I became +1, she became -1, there was an explosion that happened. You didn't see it, but there was. Energy's released. Now you want to separate us, right? You want to push me away from her? Guess what it's going to take to break the bond? Energy. It takes energy to break. Take and break round. Okay? So when bonds are formed, energy is released. And the more energy released, the more stable the bond will be. Okay? That's an important thing about energy. So you'll see questions like, turn in your bonding packet. I know there's one. You'll see questions like, thank you for the electron. Number, I'll find one real quick. 4. Look at number 4 and answer it right now. So which statement describes what occurs as 2 atoms combine to make a molecule? Robbie, what'd you put? B. B?
No, I said B.
Oh, thank goodness. D is correct. A bond is formed, 2 atoms become a molecule. You're making a bond. And whenever you make bonds, energy is released. Whenever bonds are formed, energy is released. If you want to break the bond apart, it takes energy. So you know too, when energy is released, it appears on this side of the arrow, right? That means it's exothermic, right? Going with kinetics, that means delta H is negative. Oops, not -1, just negative. Okay? So what we had is bromine got together with bromine, right? And I'll show you how that works in just a minute, to make the molecule Br2. And when that happens, energy is released. And why would energy be released? Because now they're more stable. So they give off energy, they're now more stable. The lower energy you have, the more stable you are. People that are high in energy, they're all squirrely and crazy, right? Okay? So whenever you make a bond, the compound is always more stable than the individual elements, because now the elements are happy. Happiness to an element is 8 in its outer shell, and now this guy has 8 in its outer shell. Okay? Questions? So that's why bonds form in the first place. Everybody wants to look like the very last column on the periodic table. Everybody wants to have a full outer shell of electrons, which we call a noble gas configuration. And they all, well, helium has 2, but the first shell's full with 2. Every other shell is full with 8. And all those guys in group 18 have 8 in their outer shell. They're happy, they're stable. They don't make compounds, not naturally, which is why if you breathe in helium for a balloon, it's no big deal. It's not going to react with anything in your body because it's happy and stable. The big deal is if you're not breathing in oxygen. That could hurt you. But breathing in helium, no worries. All right. There are types of chemical bonds, and I'm going to kind of just do this as a flow chart. If you want to copy it, great. Everything that I'm about to write is written in words, but I think sometimes pictures are better than words. So there are really 3 types of chemical bonds, 2 major types of bonds. A bond is just a force of attraction between atoms. Remember me and Stace, I'm positive, she's negative? It's just a force of attraction between atoms. That's the first type, ionic. Ionic, in general, we say are formed between a metal and a nonmetal, right? Because the metal gives its electron or electrons to the nonmetal. So the metal becomes positive and the nonmetal becomes negative. So what you need to know about ionic is that they're formed by the transfer of electrons. Straight up give it. No sharing going on. I gave my electron to Stacy. She's positive. I'm positive, excuse me, she's negative. But it doesn't just have to be between a metal and a nonmetal. Really, any plus-minus bond is ionic. So you could have a positive metal and a negative polyatomic. Polyatomics are found in reference table E as in Edward. Okay? For example, if you had like KNO3, this is your metal, this is a polyatomic. I always tell my students, if you see 3, as in 3 capital letters, go to table E, because chances are it has someone from table E. Now, that excludes organic chemistry. Okay, so for those of us that are starting to learn about organic chemistry, that's not included. Organic's a whole different situation. Carbon-based compounds are different. Okay, but if you see 3 symbols, 3 capital letters, you know you have a polyatomic in you from table E. This is potassium nitrate. There's an ionic bond between the K and the NO3, because this is +1 and this is -1. And opposites attract, that's your ionic bond. Okay, this one also happens to have a covalent bond within the polyatomic. This is a nonmetal, this is a nonmetal. So when you have 3 capital letters and there's a polyatomic in there, that has both ionic and covalent bonds. The attraction between the ions is ionic. The bond within the polyatomic is covalent. They ask that question a lot too. I'll show you that in just a minute. You could have a positive polyatomic and a negative nonmetal. There's only one positive polyatomic. It's ammonium, NH4. So you could have something like NH4Cl. Again, this is +1, this is -1. That's an ionic bond. Within the polyatomic, nonmetal to nonmetal, covalent. Okay? But there is an ionic bond here. You could also have 2 polyatomics. You could have a positive polyatomic and a negative polyatomic. All of these contain ionic bonds, okay? And that might be something like NH4, NO3, ammonium nitrate, okay? Common in fertilizer and in making bombs. Okay, the bond between ammonium and nitrate, because ammonium's positive and nitrate's negative, this is +1, this is -1, that's ionic. Within the polyatomics is covalent, but the attraction between oppositely charged ions makes an ionic bond. Things with ionic bonds have particular properties. Like, and I have them in a table for you, they have super high melting and boiling points. You cannot melt. Our most common ionic compound, I think I didn't even, metal, non-metal, NaCl, table salt. You can't even melt that on your stove. It doesn't get hot enough. My Bunsen burners don't get hot enough. Go home and try it. Put some salt in a pan and turn your burner on high and it will not melt. The melting point of salt is somewhere around 800 degrees Celsius. Remember ice, water, melts at 0. Okay? This melts at 800. Super high melting and boiling points. The other thing you should know about ionic compounds is that they don't conduct electricity as solids. Because what do you need to be able to conduct electricity? Moving charged particles. And if you're in the solid phase, even though you're made, remember Stacy and I on plus, she's minus? In the solid phase, all we do is this, we don't move. Okay? So you need to melt us so that we can act like liquids, or dissolve us in water to break down the ions. If you do that, then we conduct. So ionic compounds, I tell you this because you might be walking down the street and find some white powder. You might want to go, gee, what kind of bonds does this have? You can identify it based on its properties, right? You can try to see if it conducts electricity. In the solid phase, ionic won't, but they will if you dissolve them in water. You can try to melt it. Covalent things will melt. Ionic things won't. Their melting points are too high. So they have crazy high melting points, and they conduct when you dissolve them in water or when they're melted, okay? Then you have covalent bonds. If you have a co-worker or you're co-presidents of your class, what do you do with the work responsibilities? You share them. Co means share. So covalent bonds are formed by the sharing of electrons. Between who? Non-metal to non-metal. Two things that are gainers, right? Let's make Stacy chlorine still, and now I'm fluorine. I have 7 in my outer shell. She has 7 in her outer shell. I want one to be stable. She wants one to be stable. Neither one of us is going to lose, but we're going to compromise. I'll let you share mine. Ew, you were chewing on it. If you let me share yours, now her electrons in my outer shell and I'm happy, and my electrons in her outer shell and she's happy, right? We complete each other, right? We share electrons. That's a covalent bond. It's the sharing of electrons between two nonmetals. It's always non-metal. Nonmetals are to the right of those stairs, everybody. On the periodic table, that jagged red line, nonmetals are to the right, metals are to the left. There are some exceptions, okay? Like hydrogen. Even though hydrogen's to the left, it's a nonmetal, okay? And there's those semi-metal things, or metalloids. Okay, that's coming up in periodic table, but those touch the stairs and the middle two below, Ge and Sb. So B-S-I-A-S-T-E-A-T, Ge and Sb. Just think of those in terms of bonding as nonmetals. They make covalent compounds. They share to be stable. Okay? Now, there's different types of covalent. That's what confuses us. Now, I'm talking bonds. There are nonpolar covalent bonds. I'm not talking molecules yet. I'm talking bonds. There are nonpolar covalent bonds, and there are polar covalent bonds. Again, I have it all outlined in word form on your little review sheet, but I kind of like it to have it everywhere, like right here in a picture. What's the difference between those? How do you know if you have a nonpolar covalent bond? Because you're going to get a question. I bet you I can find one right now. Let's look at it. Let's find one. Yeah, and now I can't find it. I didn't give you one of that? That's crazy if I didn't. I'll have to get you some of those. Friday, I'll get you some of those. Oh, where'd the rest of the answers go? Yeah. That's interesting. Yeah, I'll get you some. Don't worry. All right, this question's not here, but it's usually here. I'll have to get you some more questions for Friday. Friday, I figure we just do, if you're going to be here, we just do more questions. And I'll get you the answers. I think do they go in order? I think what happened is 2 of my pages got eaten by the copier, because if you notice it goes from 14 to 29, and then it goes from 43 to 51, and then my answers are missing. So I think the copy machine, I probably programmed it wrong, to be honest with you. kind of ate some questions, but don't worry, I'll get you some. How can you tell if you have a nonpolar covalent bond? Anybody know? No, now you're talking molecule. Bond.
The way they share.
Okay, the way they share, which is equally, and the way you know is, it's a nonmetal bonded to itself. It's two of the same nonmetal. Can you name anything that's bonded to itself? By the way, that's equal sharing, right? Oxygen, right? O2. Oxygen is O, it's double bonded to itself. So there, oxygen has 2, 6, right? That's its electron configuration. It's not happy by itself, right? It needs 2 more to be stable. So instead of, like I did with Stacy, instead of let me share 1, you share 1, oxygen says, I'll let you share 2 of mine if you let me share 2 of yours. So what ends up happening, pretend she has 2. What ends up happening is, if we just look at the outer shell, I'm just going to do this. Lewis dot diagrams for elements, okay? They share this, they share this. So they come close enough so that those overlap, right? And now when we draw the dot diagram, we put the shared electrons in the middle. Okay? So now this is this oxygen's outer shell with 8, and this is this oxygen's outer shell with 8. Now, the reason it's called equal sharing isn't because they both brought 2 to the party. The reason it's called equal sharing is because they're both attracting those electrons with the same force. What do you call the ability to attract electrons? Electronegativity. They have the same electronegativity. So this oxygen is tugging on those electrons with the force of like 3.5, and so is this guy. That's its EN, electronegativity, ability to attract electrons. So Stacy and I are sharing 2 pairs of electrons, and she's pulling on them with the force of 3.5, and I'm pulling on them with the force of 3.5. It's like playing tug of war with yourself. Where do the electrons stay? Right in the middle of the bond. That's why it's equal sharing. Those electrons are going to be equidistant between this electron, or this oxygen, and that oxygen. They will stay right in the center of the bond. Nobody wins a tug of war. Okay? As a result, since the electrons stay right in the middle, you don't get any partial charges. There ain't no poles created in a nonpolar bond. Nobody's negative, nobody's positive. And so if you have a nonpolar bond and you don't get poles, then overall this guy is a nonpolar molecule, because there's no partial charges to begin with. So anytime you have a nonpolar bond like this, you always, always, always create nonpolar molecules. Always. Nonpolar molecules have no overall charges. Well, if you didn't have any to start with because you shared equally, you're not going to get any. Right? That's it. No overall charges. Okay? That's the bottom line. So any diatomic, obsessed Cleveland Browns fans have no intelligence. Right? Those are all the things that bond to themselves. They're in masking tape up there. Starting at atomic number 7, see with nitrogen, atomic number 7, they make a 7. NOFClBri, but that's only 6 of them. Where's the 7? H. And so the mnemonic is obsessed, Cleveland Browns fans have no intelligence. Obsessed, oxygen, Cleveland chlorine, Browns bromine, fans fluorine, have hydrogen, no nitrogen, intelligence, iodine. Notice most of them are halogens, group 17 elements. Okay? You have to know who they all have nonpolar covalent bonds. They all are nonpolar molecules. We're doing organic chemistry, my students, now. Let's talk ethane. Right? F, 2 carbons, ane, all single bonds. Nonpolar covalent bond. C bonded to C. Okay? Anybody bonded to themselves is a nonpolar covalent. Any nonmetal bonded to itself is a nonpolar covalent bond. Okay? So this bond is nonpolar covalent. In terms of the regions, and I don't want to get into a lot of philosophical differences here, but this bond would be considered polar. In reality, most college textbooks say the difference between those isn't large enough to create poles. But Regent says that bond is polar. Okay, oh, and that's the other kind of covalent bond, right? Where are we? We said that there are non-polar covalent bonds and polar covalent bonds. These are two different nonmetals. Okay, and as a result, unequal sharing. I'll tell you where you see that. You know where you see that? Water, hydrogen and oxygen. Okay, here's hydrogen and oxygen. H2O. O, H, right? H. Okay? Let's pretend hydrogens, oxygens are the electrons are the X. I'll let you share mine oxygen if you let me share yours, so they get close enough so they overlap, so now hydrogen's happy. Right? I'll let you share mine, blah, blah, blah. You let me. Okay, so now that, and now oxygen's happy because it has 8, right? It all works out. We're going to draw these dot diagrams momentarily. But oxygen is attracting the electrons with the force of 3.5. And puny old hydrogen is only attracting them with the force of 2.1. So there's a tug of war, right? And if Stacy's oxygen, guess what? She's winning. So even though I'm sharing, she's able to pull the electrons closer to her. And she's pulling negatives toward her. So you know what that means? She becomes partially negatively charged because she's got all these negatives hanging around her head. So oxygen gets, this is the symbol, a partial negative. And hydrogen gets a partial positive. Okay? In that bond, due to the unequal sharing of electrons, because oxygen has a greater ability to attract them. It determines so much that electronegativity. It's so important. And the same exact thing happens on the other side of the bond. Right? The H gets a partial positive, the O gets a partial negative. So all the negative is on oxygen's head, and all the positive is on hydrogen. So the bond is polar because it's two different nonmetals undergoing equal sharing. Okay, now, how about the molecule? Because now, it was pretty easy. We could see that if it had no poles to begin with, it wasn't going to get poles. Right? But if it has poles to begin with, which this does, a positive pole and a negative pole, they can be arranged in such a way that they cancel each other out. This does not. Okay? So this is the confusing part. You can have, I'm just going to write it on another page, you can have polar bonds arranged with symmetry. Okay? And if the polar bonds are arranged symmetrically, then you are overall a non-polar molecule. And that's super confusing. This is so abstract because this isn't symmetry like math. Can you draw a line and fold it in on itself? That's not what we're talking about. We're talking about if the poles cancel each other out. And the easiest, you have to know which shapes are symmetrical. Okay? Here's the thing though, they give you the same molecules over and over and over again. And we're gonna break those molecules down in just a minute because I guarantee you're gonna get them. Okay? The most common examples of polar bonds arranged symmetrically are, do you know? Methane's one, right? Carbon dioxide is the other, right? Carbon dioxide is easy to see. This is what carbon dioxide looks like. It has a double bond. So oxygen's pulling this side harder, and this oxygen's pulling this side harder. So those pulls, because the electrons are being pulled this way, and electrons are being pulled this way equally, cancel out. So carbon dioxide has polar bonds, but overall is a non-polar molecule. Okay? CH4, same deal. Polar bonds, non-polar molecule. Why? Because the charges are arranged symmetrically. They cancel each other out. So even though, if you just look at a bond, there's a plus and a minus, overall in the molecule, there ain't no poles. They cancel out. The other ones, the other thing like CCl4, CF4, and I'm just going to draw them like this so you can see it easier. This one's pretty easy to see, I think. You got F pulling harder this way, you got F pulling harder this way, you got F pulling harder this way, they all cancel out. Okay? So those have polar bonds arranged symmetrically, so they are a non-polar molecule. So to figure out bond type, you want to know who's bonded to who. Two of the same or two different? Two of the same, non-polar, two different, polar. To overall figure out molecule polarity, you have to look at the shape, okay? Because the shape determines the symmetry. You could also have polar bonds arranged asymmetrically. And if that just means the charges don't cancel out, right? They're asymmetrical. And that's like, I call it linear with 2, that's like HCl. If you have H bonded to Cl, Cl just straight up pulls harder. There is nobody canceling that out on the other side. This guy gets the negative, that guy gets the positive. The bond is polar because it's two different nonmetals. The molecule is polar because nobody cancels out that pull. Nobody. Okay? Then you've got your infamous, what kind of bear dissolves in water? Polar bear. Everything dissolves in water because water's polar. Not, the bonds are polar, yeah, but it's because the molecule's polar, right? So you got your H2O. All the electrons are going this way. Nothing to cancel that out. That is polar bonds and is a polar molecule. Okay? All the electrons go up towards oxygen's head. And then finally, the one that's bent shaped. Bent is the shape. Okay? And then finally you have ammonia, NH3, not ammonium, ammonia. Nitrogen straight up pulls harder. So all the electrons are going towards nitrogen's head and there's nobody to cancel that out. That's pyramid shaped. Okay? So that means that overall charges will remain. The hydrogens here will be positive, the nitrogen will be negative. The oxygen here will be negative, the hydrogens will be positive. Okay? So you must absolutely know that water has polar bonds and is a polar molecule. Ammonia has polar bonds and is a polar molecule. CF4, carbon tetrafluoride, has polar bonds but is a non-polar molecule. You know what this shape is? Tetrahedral shape. Yep. Tetrahedral shape is always a non-polar shape. Okay? That's always non-polar. So I don't know how to summarize it. I mean, I could give you the ones, I really did give you the ones they always ask. Okay? I don't know if I included anybody on here because it probably was on the page that got cut off. Nope. I promise to get you more of those. Strength. Diagram for CF4. Yeah, I'll have to get you the rest of those. So you got to know if they ask you for a non-polar molecule. Say they ask you for a non-polar molecule. Which of the following is a non-polar molecule, right? You want to look for a diatomic first. Find the easy ones because they have non-polar bonds. So look for a diatomic like H2 or N2 or something like that. If they're not there, look for carbon dioxide. Okay? Because carbon dioxide is a nonpolar molecule. That's why your pop doesn't stay fizzy. Because the carbon dioxide that's nonpolar doesn't want to stay dissolved in the water that's polar, because like dissolves like, and carbon dioxide doesn't dissolve well in soda. That's why we have to bottle it under pressure. When you first buy a soda, the bottle's super hard, because we force that carbon dioxide in. Then put the cap on real fast. Okay. Then when you open the cap, what happens? Whoosh, the carbon dioxide comes out of solution, because it's nonpolar, right? And the water is polar. All right? Yes? Now you want soda? Okay. See, then if that's not there, look for something tetrahedral. CF4, CCl4, something tetrahedral. Right? CH4. Look, these are tetrahedrals, right? Look for them. These guys have polar bonds, but they are overall non-polar molecules because the polar bonds are arranged symmetrically. This guy is non-polar bonds, non-polar molecule. If they're looking for a polar molecule, you got to pick someone with polar bonds. You're going to find like HF, HCl, I hope you see a pattern here, HI, something like that. Or you're going to look for water, or you're going to look for NH3. Always they give these as your choices. Trust me, I promise to get you some for Friday. I apologize that got all screwed up on the copy. Okay? Questions about that? Questions? In order to be a polar molecule, you must first have polar bonds. You must be two different nonmetals. Okay? In order to be a nonpolar molecule, though, you may be two different nonmetals, but you are arranged symmetrically. These guys are arranged asymmetrically. Okay? So polar molecules are always asymmetrical. And it's asymmetrical with respect to charge. Nonpolar molecules are always symmetrical. So why is blah 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 a nonpolar molecule? Because it's arranged symmetrically. Okay? Why is blah 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 a polar molecule? Because its charges are distributed asymmetrically. Done. That's all you have to do. That's it. Okay, and they ask the same ones over and over again. That's the thing. So really, if you don't get it, because it is super abstract and super complicated, you have to be able to think in 3 dimensions and what these guys look like and charges pulling and this and that. And like crazy. Just memorize these ones. Just memorize them. That's all you got to do, because they ask the same ones over and over again. I guarantee you. All right. Oh, covalent things. I think we didn't talk about their properties, but like it's opposite ionic. And I have it on the table. They have super low melting and boiling points. Most covalent things, carbon dioxide, oxygen, nitrogen, they're gases already. Not only have they melted, they've also boiled, right? Most covalent things have super low melting and boiling points. And they never conduct in any phase, not as solid, not as liquid, not as aqueous. They don't conduct because they're not made of moving charged particles. The exception to that is acids. Like if you have H first, like HCl, HF, HI, these guys will conduct, okay? Because they'll break apart in water. But any other covalent thing won't conduct at all, okay? And then finally, the other type of, it's kind of dumb that we even count it as a bond because it's so lame, but it's important, metallic. And everybody thinks metallic bonds are bonds between metals. Never. Metals don't make bonds. Because I want to lose and you want to lose. How can we satisfy each other? We cannot. Okay, so a metallic bond is a bond within a single metal. And they're really due to mobile valence electrons. That's what you need to know about metallic bonds. Positive ions floating in a sea of mobile electrons. Mobile valence electrons. That's what makes a metallic bond. Okay? But metals have really high melting and boiling points, just like ionic compounds do. And what distinguishes them, well, other than their luster, they're super shiny, okay, and they're malleable, but you can't really hammer salt into a shape, okay, is that they can conduct as solids because they have mobile valence electrons, whereas ionic things cannot conduct as solids. So that is a distinguishing property between metals and ionic compounds. Yes? They like to ask a lot of questions about that. Anything else I want to say about metallic bonds? I don't think so. Let's draw some dot diagrams. I think we have something like that coming up. We did all this. We did all this. We did this. We did this. Okay. Lewis dot diagrams. There's one number 8. Which of the following Lewis dot diagrams represents calcium oxide? And then I know there's another one, number 51, where they ask you to draw it. Okay? Oh, I should go back real quick. These covalent compounds are called molecules. So the word molecule automatically means it has covalent bonds. Okay? So there's really 2 types of compounds, ionic and covalent. Metals are elements. These are elements. Okay? The way you draw a Lewis dot diagram depends on what kind of bonds you have. Because you're either going to show transferring if it's ionic or sharing if it's covalent. Okay? So when you are asked to draw a Lewis dot diagram like in number 8, you got to ask yourself, what kind of bonds does this have? So what kind of bonds? They give calcium oxide, right? What kind of bonds does it have? Well, it depends. Is it a metal to a nonmetal or a nonmetal to a nonmetal? So you need to code it. Calcium's to the left of the stairs, that's a metal. Oxygen's to the right of the stairs, that's a nonmetal. So I am showing ionic bonds, which means I have to show transfer. So how do you do that? You must show charges, subscripts, I spelled that wrong, and put 8 dots around your nonmetal. That's what you do. So what's calcium symbol? Anybody know? Ca. Okay, what's oxygen symbol? O. Okay, we need proper charges. You know where we got those? The reference tables in the box for calcium, in the box for oxygen. There will be a number, and that is what you need to show. Okay, so we're going to go here to our reference. Oh, maybe. Wow. Get out. All right, we'll just close you because you're driving me crazy. And reference tables, we go to our periodic table. And if you look there, you should find calcium in compounds is +2. That means, see how it's 2882? In order to become happy, it has to lose those 2. So it's going to off those 2 electrons when it's stable and in a compound. And then oxygen over here has 2, 6. It means it needs to gain 2, right? And it'll take on the -2 charge. So you just slap those charges up there. So it's ionic, it has to show charges, which means right away you should eliminate A and C because they don't have charges, right? If it's ionic, you need charges in the dot diagram. Then, since the metal gives its electrons to the nonmetal, we give the nonmetal 8 dots. Done. That's it. That's all you need for an ionic dot diagram. Super easy. I have another one here, calcium chloride. So we write the symbols. We look up their charges. All right, this one's a little different because now the charges don't equal 0, right? So calcium wants to lose 2, but chlorine only wants to gain 1. Well, then you're going to need 2 chlorines, right? Because it'll give 1 to one chlorine and then 1 to another. In other words, if the charges don't equal 0, y'all remember what to do? Crisscross. You will need 1 of these and 2 of these. Stick 8 dots around your nonmetal. Done. Dot diagram, calcium chloride. So you need proper charges, proper subscripts to make a neutral compound, 8 dots around the nonmetal. The harder dot diagrams are for covalent. Okay, now I don't know how Ms. Saccone told you to do them. I do this crazy math thing. So you can do it your way or my way. I don't care. I do math, okay, because I'm not really afraid of math. So I do valence electrons. So I look up carbon, and I write down how many valence electrons it has. Remember, valence electrons are the electrons in the outermost energy level, right? The last number in the electron configuration, those are your valence electrons. So carbon has 4, and then you have 2 oxygens that each have, how many valence electrons did oxygen have? 6. Oh dear. So 4 plus 2 times 6. So 4 plus 12 gives me 16 valence electrons. Which means when I draw my dot diagram, there have to be 16 dots. Okay, or the equivalent of 16 dots if you're using lines. Then you do happiness. How many do they have when they're happy? And for everybody it's 8 except hydrogen here. Hydrogen's happy with 2. Everybody else is happy with 8. Okay, so for happiness, it's 8 except hydrogen. H is happy with 2. Okay, helium too, but it's not going to make bonds, so we don't need to worry about dot diagrams for it. So carbon's happy with 8, plus there are 2 oxygens that are each happy with 8, so that's 24 for happiness. Okay? Then you subtract those. 24 minus 16, and you get 8, and divide by 2. That means we had better have 4 bonds in our picture. Okay? Subtract, divide by 2, that gives you the number of bonds. Put the element that there's less atoms of, unless it's hydrogen, in the middle. Put the others around it. Right? 2 oxygens. And connect them now with 4 bonds. A bond is a pair of electrons. Okay? So I'll do 1 bond, right? 2 bonds. Uh-oh. Gotta go back. 3 bonds. 4 bonds. You can't add more oxygens because the formula is CO2. You only have 1 C and 2 O's. You have to connect them with 4 bonds, which means there is a double bond between carbon and oxygen. Actually, 2 double bonds, right? 1 on this side, 1 on this side. Okay, now, I just got done telling you your picture needed 16 dots. Right now, my picture only has 8. Okay, carbon's perfectly happy, right? Isn't this, you don't have to draw this, but this is carbon's outer shell right now. 1, 2, 3, 4, 5, 6, 7, 8, right? Problem is oxygen's not happy. So after you do your bonds, you go and fill in with what we call lone pair electrons so that everyone is happy, okay? So oxygen right now is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. The shared electrons, those bonding count, the bonding electrons, the electrons that are being shared, count towards carbon and towards oxygen. I'll let you share mine if you let me share yours. So they're overlapping in the orbital space. They count towards both. So this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So now, this is this oxygen's outer shell and it's happy. This is this oxygen's outer shell and it's happy. And our picture now has 16 dots. You don't have to draw those circles. I'm just showing you how they're happy. Okay? So it really looks like, if you don't like to draw dots for bonds, you can draw lines, right? You can do 1, 2, 3, 4. And then when you go back and fill in, oxygen has 2, 4, 5, 6. You have to remember a line is 2. That's the dot diagram for carbon dioxide. The other thing you can do is look at how many more it needs to be stable, and that's how many bonds it's going to have to make. Carbon has 4 valence electrons, which means it has to form 4 bonds to be stable. Oxygen has 6 valence electrons, which means each oxygen needs to make 2 bonds to be stable. That's another way to figure it out, and then you can put them together that way. Okay? Look at number, what did I say, 51 for the CF4. Okay? We'll do one more of these. And I want to talk about IMS. I think we'll have time to squeeze it in. And then Friday, if you come, it'll be only practice. If you don't come Friday, then it's okay. You can come get the practice with proper answers. Okay, but it's kind of good to get through it all here. They want the dot diagram for this thing. What do I have to do? Uh-oh. What do I have to do? How do you know you have to do valence electrons? Aha! We got to figure out, do we need charges or we got to do all that math crap, right? So the way we do is by coding it. You got this thing that's a nonmetal, that thing that's a nonmetal. That's covalent. That means we got to do the math crap, right? Okay, so now we do the valence electrons. Carbon has 4, plus there are 4 Fs that each have 7. 7 times 4 is 28. 28 and 4 is 32 valence electrons. If your math skills are not up to mine, don't worry, you'll get a calculator for this exam. Bring one, actually. It cannot be a graphing calculator. Graphing calculators are barred from the exam. Happiness. Everybody's happy with 8, except hydrogen. So carbon's happy with 8, plus there are 4 Fs that are each happy with 8. 4 times 8 is 32. 32 and 8 is 40 for happiness. So obviously we don't have enough. We're going to have to share. Okay? My father's taking care of my children. My daughter has to go to piano, so I'm a little nervous that this is a uh-oh, couldn't find the piano place. But it's okay. Subtract these, right? 40 minus 32, you get 8. Cut it in half, you need 4 bonds. You put the element there's less of in the center. Pretend it's in a box. Put the other F's around it. 1, 2, 3, 4. Connect them with 4 bonds. Now you want to do a pair of dots? You want to do lines? Anybody have a preference? Dots. Dots? Okay. 1, there's 1 bond. 2, there's 2 bonds. 3, there's 3 bonds. There's 4 bonds. If it needed 6, I'd go back around. 5, 6, right? You put another pair there and another pair there, but we don't need that. Okay? Now, fill in so that everybody's happy. Carbon's good to go. You see the 8 dots around it? It's all stable and set. Fluorine is not. It only has 2, so it needs 6 more. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You count them, you better have 32 dots, and indeed you do. That is the dot diagram for CF4. Okay? Carbon needs to make 4 bonds, F needs to make 1 bond. That kind of shows you what you need to. All right? Questions on that? I promise to throw you a whole bunch more questions. What I did want to talk about then, we have about 3 minutes left, and I think I could do it, are IMFs. That is the other thing that this unit talks about, intermolecular forces of attraction. It's not a bond between atoms anymore. It's why one water molecule loves another water molecule, right? You've seen it happen. Do you ever have a drink on a hot day, you put it on a coaster, and you pick up your drink and the coaster sticks? Hydrogen bonds. That's why water's sticking to itself. That's why the coaster comes up. It's a force of attraction between water molecules and the coaster that cause the coaster to come up. So these are forces of attraction between whole molecules. These are why molecules love themselves, why they stick together, okay? Or don't. Some molecules do not. Like nail polish remover, that's why it's super stinky, right? It evaporates easily. It doesn't care about itself. Okay, alcohol, like rubbing alcohol, doesn't really love itself. Okay, those have weak forces of attraction. So these are attractions between whole molecules. This is what you have to know. The strength of the IMF determines vapor pressure, the pressure of the gas. It determines boiling point, and it determines the spacing between molecules in the liquid phase. If there are strong IMFs, then the molecules love each other. They get really close together, and they're hard to separate and evaporate. So they have a high boiling point because they don't want to be apart. They love each other. They cling to each other. So to separate them to become a gas is difficult because they love each other. Okay? It's like people in the hallway in the spring. Okay? Nick, you're going to see her in 45 minutes, right? Strong force of attraction. They love each other. They don't want to separate and leave and go to other classes or become gases. So they love each other. They stick together. Okay? So strong IMFs, the higher the boiling point. Explain in terms of intermolecular forces of attraction why the boiling point of blah, blah, blah is higher than the boiling point of blah, blah, blah. The first blah, 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 the one with the higher the boiling point, has stronger IMFs. That's all you need to know. The higher the boiling point, the stronger the IMFs. The lower the boiling point, the weaker the IMFs. Okay? Lower vapor pressure because they won't leave and become gas. What are IMFs? I put 3 basic types here, and they are in order from strongest to weakest. Number 1, most important, hydrogen bonds. Not everything with hydrogen has a hydrogen bond. Hydrogen bonds only form between H and O, H and F, and H and N. I think of them often, right? OFN, remember? Or, boy, babe, those hydrogen bonds, they're sure fun. They're certainly fun. Or perhaps by now you've had just about enough of hydrogen bonds. But those are the only things that can make hydrogen bonds. And FYI, if we got water, this is not a hydrogen bond. That's a polar covalent bond between 2 nonmetals, 2 different nonmetals, right? It's not a hydrogen bond. This is a hydrogen bond. When the H of one, because of its partial positive charge, is attracted to the negative O, F, or N of another. Okay? Hydrogen bonds are really strong IMFs. They give water its unusually high boiling point because most things like water, covalent, are already gases. Can you imagine if it weren't for hydrogen bonds, we would not have a liquid water. We'd have gaseous water. Okay? If it weren't for hydrogen bonds, the liquid phase of water would not be more dense than the solid phase. That's unusual. Solids are more dense than liquids, except for water, because water has hydrogen bonds. And then the Titanic never would have sunk, because ice floats. Isn't that weird? Solid water floats in liquid water. That's abnormal. Okay, go.
What's that symbol?
Partial. Partial positive, partial negative, due to the differences in electronegativity. Okay? It's like a 8 that's incomplete, like a lazy 8. Okay? Not a crazy 8, a lazy 8. So the hydrogen bond is between the molecules, not within the molecule, between. O, F, and N make hydrogen bonds. Gives them an unusually high boiling point. I promise I'm almost done. By the way, if you need to know why it's O, F, or N, it's because they're small and they have super high electronegativities. So they can make strong partial charges. Dipole, dipole. Dipole is my favorite non-bad word, bad word. So like somebody makes you mad, you call them a dipole, it sounds really bad. It's better than in front of your children calling anybody a bleep hole, right? You call them a dipole. So these are attractions between polar molecules, okay, like HCl has these. And then van der Waals forces are the puniest, and they're forces of attraction between nonpolar molecules, like carbon dioxide likes itself, but not as much as water. because this is a weaker IMF. Chlorine, all the noble gases have van der Waals forces. What you need to know about them, other than they're between nonpolar molecules, and that they're weaker than these ones, is that the bigger the nonpolar molecule you are, the more electrons you have, the stronger your van der Waals will be. Like, for example, iodine has stronger van der Waals than fluorine, which is why iodine is a solid at this temperature. Did the lights just go out? Or were they out? That's why iodine is a solid and fluorine is a gas, right? Because this has, I don't know, lots of 53 times 2. This has 106 electrons, and this only has 18 electrons. Okay? So when it comes down to van der Waals, their strength is determined by how many electrons they have. Bond polarity too, remember, and this is the last thing, I promise. I know I've said that like 17 times, but this time I really mean it. Remember we talked about polar covalent bonds? One thing you should write here is the greater the En difference, the more polar the bond. They ask that a lot too, which I will show you everything that they ask on Friday. And we're like 2 minutes over, and I don't want anybody to miss the bus because I can't drive you home. So thank you for being patient. That's everything I promise you need to know about bonding, and on Friday we will apply it. Okay? And I'll give you questions that actually have answers. I hope I crammed a lot into your head today. Yes? No? Yeah. Good.